Hello, in this video, I want to introduce work as a concept, define it, and then work through some examples. So work is a technical term in physics, and I'm going to define it in this video and explain what it is. Why we're talking about work will not immediately be evident. Work is related to energy, and we can define it as the transfer of energy from one form into another. So when work is done, energy is being transferred from one form into another form of energy. But we're not really going to see how that happens for a little bit. First, I want to concentrate on the definition because the definition is mathematical enough that it's worth unpacking on its own. So first, just a little bit of intuition to hang on to for what work is. So let's say I've got a box right here, a good old box, and I push the box. So I apply a force to the box in this direction to the right, and I push it along the ground like so, and the box travels a displacement delta x. I can say the work done on the box by this force F is equal to the force times that displacement. So work is calculated, or work occurs, or work is done, I guess I could say. Work is done when a force acts in the direction of the displacement, or the direction of motion, I could say. And that's our most basic definition. This is also kind of the simplest possible case. There's lots of more complicated cases. One thing that we'll say for sure is that work is not done when something moves, but the force does not act in that direction of motion. So another example that I could have, if I had a similar example here, so if I copy this, let me paste it and copy it. All right, so looks the same. Let me erase the force. I'll move my box back to the starting line. So let's say I'm applying a force this time that looks like this. So I'm applying a force up on the box. There's lots of other forces that could be acting here that I'm not considering. I'm just considering one force, and we can say the work done by that one force acting on the box. So this force F, this purple force F, might do work on the box, but if the box moves this way, so the box moves through this displacement, then the work done on this box will be 0. Work is not done by a force that acts perpendicularly to motion. I'll write this little perpendicular symbol, acts perpendicular to motion. So in the first case here, we had work done because the force was acting in the direction of the displacement. In this case, we had no work done because the force was acting perpendicular to the displacement. In general, I could write down a third case. So a third case here would be that if I have another case here. So a slightly more general case, let me move my box back to the starting line. If I have another force in a different color that I haven't tried yet. So if that force looks like this, and that force makes an angle, say theta with the horizontal, and I move my box through this displacement all the way over here, then in that process, the work that is done is equal to F cos theta times delta x, because the component of the force that acts in the direction of motion is F cos theta. So the part of the force that's relevant for calculating the work is just the part that acts in the direction of motion. Okay, so we're getting work by multiplying force that acts in the direction of motion by the displacement in that direction. That's how we're calculating work. All right. So that's a starting point for work. One thing we can note about the units of work, units for work, which we should probably look at because they're a little bit weird. So you'll notice here we've got a force times a displacement. So the units for work are, I guess I can say units for work are newtons, that's a force, times meter. That's called a joule, which is usually just written J. You'll notice that, or some of you may notice that this is a unit of energy, and we're going to talk about that in a little bit. All right, so this is just kind of like a little bit of intuition about how work works. And I want to give you a formal definition of work now, and give me a second to write that down. All right, so I have I have an equation here and I have a little graph. So let me explain. This is the formal definition of work. Work is equal to this integral expression. I have a force. This is the force that will be doing work on whatever object we're considering. This is dl. This is a little displacement vector. It's a tiny infinitesimal displacement vector along some path that we're taking. And I have a starting and ending point for the motion. So on my little graph here, I've got a little XY plane. So I'm looking at, on this graph, I'm looking at the trajectory of something through space. In the previous examples, that would have been the trajectory of the box, but we're generalizing here. So let's say I've got a path, and the path that my object takes through the space can be whatever I want. I'm gonna draw like kind of a curvy path. So there's some object, it started at point A, and then it moved along this path to get to point B. Along the path, there was some force F acting on it. So let's say at this point, for example, our force was acting on this object. And it could have been acting in whatever direction. I'm going to draw it in this direction. And the force could be changing along the path, might be constant. We don't really know anything necessarily about the specific force that's acting on our object here. We just know there's some force acting. And there's a little dl. So the dl is a tiny section of the path. It's a little vector that points in the direction of the path, for that tiny section of the path. And it looks like that. So there's this little tiny infinitesimal piece of path. Right here, it points in this direction because that's kind of tangent to the path there. If I had chosen this little section of the path, my dl would point this way instead. If I'd chosen this little section of the path, my dl would point this way instead. It's always just going to point along the path wherever you choose. And it's just a little displacement vector. So what I'm doing is I'm taking a dot product between the force and the little displacement at every section along the path and then adding those up. So the way to think about what the integral is doing is it's adding up the contributions of all these little calculations of the dot product of F and the displacement at every section along the path. That's what this integral expression is doing. If we go back to our last example, you might recognize something that kind of looks like the dot product. If you take a dot product of two vectors, one way to write down the dot product is the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them. You'll notice that this kind of has that form. In this case, where we are applying a constant force F, if we take the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and the displacement, basically we've taken a dot product of the force vector and the displacement vector here. Secretly, that's what we did above. This is a special case of this equation below when the force is constant along the path. If the force is constant along the path, then we can kind of pull this out of the integral. And then when we integrate all these tiny displacements, we just get the total displacement of the path. Okay, we're gonna keep looking at this and working with it, interpreting it, but this is a place to start. So as a reminder, what we're doing is we're taking the force at a given point along the path, dotting it with the displacement vector at that section of the path. When we do the dot product, we ask kind of whether the force is perpendicular or parallel to the path at that point. And then we add up all those tiny little contributions, the whole path, and we get the total work done by that force along the path. All right. What I want to do is show you some examples. So I think some examples of how this works in practice is the best way forward here. So I'm going to do that. Give me 1 second to get that set up. All right, so I've got a little picture here. I have my little XY plane, and I've got a little square blue box here. There's some force acting on the box. There could be other forces acting on the box too, but the only one we're going to consider for these calculations is this force. We're going to calculate the work done by this force as the box moves from the origin, say 0, 0, to this point out here, 4, 2 in space. So I've got my XY plane here. We're going to consider, you might notice in my previous diagram that I had to draw the path from my starting point to my ending point in order to actually think about defining the work, because I need to consider what the force is doing at every point along the path. And that's true here. So in order to calculate the work done from here to here, I need to know what path I'm taking from my starting point to my ending point. And I'm going to consider a particular path that looks like, so my first path, actually, maybe I'll just draw it on the drawing. So let's say I've got a purple path. So my purple path looks like this. I'm going along the x-axis this way, and then going up this way. So it's kind of a two-part path. You'll notice like there's no way that this could be the only force acting on the box. There must be other forces if the path I'm going to take looks like that. But again, we're only considering the work done by this particular force for this problem. So this is not the net force. It is just a single force acting on this box. And we're asking how much work has been done by this force along this purple path from 0, 0 to 4, 2. So we're going to do this. So I'm going to, this is for the purple path. Okay, so what we want to do is calculate the work. We've got this expression to start with. And what we want to do is we want to figure out first, what is even DL? What does DL represent here? Well, DL represents a little bit of the path. So our path is really in two parts. We've got a horizontal part and a vertical part. And so along the horizontal part, the path, the DL always points horizontally. So the whole time from 0, 0 to 4, 0, the DL, our little tiny displacement vector, always points horizontally, but we're just taking little tiny horizontal chunks of the path. And so I can say the little DL vector is a little change in x, dx, that points in the x direction, x hat. So x hat is just the unit vector in the x direction. And so that's for the horizontal part. For the vertical part, it looks different. For the vertical part, the DL points upwards. And so the little tiny path vector there, displacement vector, is dy y hat. So a little change in y in the y direction. That's what the little path length vector DL looks like for that case. So the way we're going to approach this problem is we're going to calculate the work done from 0, 0 to 4, 0 using this DL, and then calculate the work done from 4, 0 to 4, 2 using this DL. So let's look at how that works. So the work will be kind of the work done along the horizontal path from excuse me, from 0, 0, that's where we started, to 4, 0, that's where we'll end along the horizontal path. Our force vector dotted with the dl, which is dx x hat. And then we have another section of the path where we're going from 4, 0 to 4, 2, where we're taking f dotted with the path length vector there, dy y hat. Okay, this is something that we can actually make some progress on now, because this is an operation that we can do. We know what f is. We're given f as this vector. So if we do 2x hat plus y hat dotted with dx x hat, to try to calculate what should go into this integral here. Well, when we do a dot product, we can take the component in the x direction of the first vector times the component in the x direction of the second vector, multiply those two things together. So 2dx, and then plus the component of the y component of the first vector times the component of the y component of the second vector, but there is no y component for the second vector. It's just 0. There's a 0 y component for the second vector. So that next part is 1 times 0. And this dot product is just 2 times dx. So what is going to go into the integral for this part is just 2dx. For the second part, we have a similar dot product, except it's f dot dy y hat. So we can do that part. F dot dy y hat. Similar story here, except now there's no x component for the second vector. So if I do the x component of the first times the x component of the second, I get 2 times 0. But then the y components get 1 times dy. So this is just dy. So the work done here should be the integral of 2dx plus dy. And the bounds now are explicitly in terms of x and y. So this is an integral over x, this first one, and the second one is an integral over y. And the bounds should reflect that. So I'm going from 0 to 4 in x along the first path, and from 0 to 2 in y along the second path. And so I've written the bounds that way. These integrals are pretty straightforward. So if I take the integral of 2 dx, I get 2x. 2x evaluated from 4 to 0 gets 8. And then the second, I've got dy, so that gets y. And then y evaluated from 2 to 0 gets 2. So the answer here is 10 joules. There's been 10 joules of work done along this path. Okay, so great. I'm going to do the same calculation again, except along a different path. And I want to show you how that works. So what if instead of going along this purple path, I take a red path, and the red path, rather than going horizontal and then vertical, just goes in a straight line from 0, 0 to 4, 2. So red path. Try to squeeze in the red path down here. All right, so we're going to try to do the same thing, except now the DL is going to look a little bit different. So here, the DL never changes direction. It always has the same direction. The red DL looks like this. And there's, on this little path, DL, this little displacement, it's not purely a change in X or purely a change in Y. It's kind of both. And the way we represent that is with a path length displacement vector like this. So there's a little change in X along this path, X hat, and a little change in Y, Y hat. So in general, this is always going to be true for some kind of two-dimensional path. You just say there's a little change in X along this path, that's in the X direction, and a little change in Y along this path in the Y direction. We could draw this out with a triangle. If I kind of zoomed in on this and blew it up. So what this looks like is DL is going this way. And what we're saying is there's a little dx x hat here and a little dy y hat here. So kind of three sides of a triangle where DL is the hypotenuse of the triangle. And we're saying this is kind of the change in the path in the x direction, and this is the change in the path in the y direction. Okay, so for us, how do we deal with this? Well, it's a similar story where we start with work equals force dotted DL along our path from 0, 0 to 4, 2. But now this dot product is going to be a little bit different than the dot products we did before, because DL has both an x and a y component. So when we do f dot DL, 2x hat plus y hat is the force, dotted with dx x hat plus dy y hat. Well, I'm going to get the x component of the first vector times the x component of the second vector. That's 2dx plus the y component of the second vector times the the y component of the first vector times the y component of the second vector. So that's dy. So my dot product now has a dx and a dy in it. And my integral, if I plug this back in here, becomes integral 2dx plus integral dy. And you'll notice actually that this now looks identical to what we had before. I've just kind of taken the integral and split it into two parts, because really it's easy to just separate this one. This is now an x integral. This one is now a y integral. Just taking what I got here and plugging it back in. So again, the bounds are going to be along the path, x changes from 0 to 4. It doesn't matter that y is also changing from 0 to 2, because the first one's just x, so only the x bounds matter here. And here only the y bounds matter. Doesn't matter that x is also changing from 0 to 4 at the same time. The way this works out, we're kind of doing them independently. So you'll notice that actually this work and this work are just the same. It ends up working out to be the same. So in this case, the work ends up being 10 joules again. In both cases, the work was 10 joules. In this case, it didn't matter what path we took to get from point A to point B, or from 0, 0 to 4, 2. Both the purple path and the red path are the same. But in general, for other kinds of forces, that won't always be the case. And we're going to look at an example soon where changing the path does in fact change how much work is done by the force. So this is just a brief introduction to working with work and how you actually do some of these integral expressions as a starting point. We'll keep working with this, and I'll see you soon. Okay, bye.